Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. AI hallucinations have caused lawyers to cite entirely fake legal cases and chatbots to recommend policies that never existed. In healthcare, an outdated model could suggest a treatment protocol from years ago, dangerous advice based on stale training data. That's the fatal flaw of a model frozen in time. And that's exactly what Retrieval Augmented Generation fixes. By the end of this video, you'll know exactly what RAG is, why it stops hallucinations, and how to wire it together yourself. You'll understand the 5 steps that turn a static language model into a dynamic, document-grounded assistant. And you'll walk away with a practical Python snippet that can start answering questions from your own files today. Large language models are frozen in time. Their training data has a cutoff date. After that point, they have zero awareness of new events, policies, or vulnerabilities. Ask about your company's new VPN policy or a security advisory from last week, and the model will guess. Those guesses sound convincing, but they're often wrong. Even the most capable models can confidently invent answers when they lack real current information. The problem isn't that language models are unintelligent. They simply can't look up information they were never trained on. Imagine asking an employee to answer every company question without allowing them to search SharePoint, Confluence, or your internal wiki. Eventually, they'd have to guess. Large language models face the same limitation. Retrieval Augmented Generation solves that problem by giving the model access to your latest documentation at the moment a question is asked. Instead of relying only on memory, it retrieves the most relevant information first, then uses that evidence to generate an answer. That's the fundamental shift from memorization to retrieval. Think of an open book exam. Instead of forcing the LLM to answer purely from memory, where it might hallucinate, RAG hands it a stack of your documents and says, "Use these." The model looks up the relevant information, reads it, and then crafts an answer. That's Retrieval Augmented Generation. Connect the LLM to a digital library, and every answer gets fact-checked against real sources before it ever reaches the user. Checkpoint. RAG Foundations. Large language models are excellent at recognizing patterns and generating natural language, but they don't verify whether an answer is actually correct. When they lack information, they often generate the most statistically likely response, which may or may not be true. A well-designed RAG system changes that by retrieving relevant documents before the model answers. Instead of relying only on memory, the model grounds its response in information from your knowledge base. While RAG doesn't eliminate hallucinations entirely, it can significantly reduce them when retrieval quality, document quality, and prompt design are done well. That's why RAG has become the foundation of many enterprise AI systems. Here's the 5-step heartbeat of every RAG system. 1. A user types a question. 2. That question gets converted into an embedding, a numeric fingerprint, and the vector database finds a handful of the most similar document chunks. 3. Those chunks get injected into a prompt template. 4. The augmented prompt is sent to the LLM, complete with the retrieved context and instructions. 5. The LLM reads the context and generates an answer, often with citations. Same flow whether you're building a chatbot, search, or compliance tool. Prompt engineering is a one-and-done move. You write a clever system prompt, but the model still reaches into its static training data. Ask about a policy that changed yesterday and it has no way to know. RAG is dynamic. Every single query triggers a fresh search of your actual documents and injects the latest context. It's the difference between memorizing a fact sheet and having a searchable knowledge base that updates the moment you drop in a new file. Fine-tuning an LLM on your data might sound powerful, but it often requires carefully prepared training data and substantial compute resources. And every time your data changes, you may need to repeat the process. That can quickly become a maintenance burden. RAG sidesteps all of it. No training runs because the latest documents are referenced at query time. For help desks, ops, and internal search, RAG is the practical path. One of the biggest mistakes people make is assuming that confidence means correctness. Imagine a network administrator asks an AI assistant how to configure a firewall rule for a newly deployed application. The model generates a detailed, professional-looking response, but the command doesn't exist in your environment because it was invented from patterns in its training data. The answer sounds authoritative, yet it's completely wrong. This is why enterprise AI systems don't rely on confidence alone. They rely on retrieval, citations, and verification against trusted documentation before users act on the answer. Let's lock in a crucial lesson. What's the biggest misconception that leads teams to trust RAG too early? Here's the heart of every RAG application. The prompt is built from 3 pieces. First comes the system instruction, telling the model to answer only from the supplied context and to clearly state when the information isn't available. Next comes the retrieved document chunks, selected by the retriever. Finally comes the user's question. Together, these form an augmented prompt that gives the language model both instructions and evidence before it generates an answer. The prompt doesn't guarantee perfect accuracy, but it strongly encourages the model to rely on retrieved information instead of guessing from memory. Watch the difference a real prompt makes. On the left, the model gets just the question. It pulls a generic answer from its training data, maybe wrong, maybe outdated. On the right, the augmented prompt includes the exact VPN policy snippet. Now the answer is step-by-step, specific to your company, and it cites the source document. That's the jump from guessing to knowing. The retriever is the component that connects your question to the right information. First, the user's question is converted into an embedding, a numerical representation of its meaning. That embedding is used to search a vector index containing embeddings for every document chunk in your knowledge base. Instead of looking for exact keyword matches, the retriever searches for the nearest semantic neighbors, identifying documents that discuss similar ideas even when different words are used. Within milliseconds, the most relevant chunks are returned and prepared for the language model. The better your retrieval, the better your final answer. Checkpoint: retrieval and vectors. A common misconception: people think the LLM does both retrieval and generation. In RAG, they're separate, and that decoupling is exactly what makes it reliable. Once the retriever grabs the relevant chunks, the generator, an LLM like GPT-4 or Claude, takes over. Its job is simple: read the supplied context and turn it into a clear, natural response. It isn't inventing steps from memory, it's translating authoritative docs into plain English. Because the retrieval step is independent, you can often swap in a different LLM with minimal changes. The key is that the model's language fluency combines with your up-to-the-minute data, so the answer stays grounded even as your documents change. And when you see the code example next, remember it's a deliberately simplified starting point. It skips chunking to keep the snippet short. In a real system, you'd add a chunking step before embedding, which we'll cover later. You can build a basic RAG system with a handful of Python lines. The code loads your documents, creates embeddings, stores them in a vector database like Chroma, and sets up a retrieval chain that pulls relevant context and generates an answer. The most common beginner mistake is skipping the chunking step. If you feed an entire manual as one chunk, retrieval becomes useless. This pattern, load, chunk, embed, retrieve, generate, is the foundation. Experiment with your own documents, but always test your chunk size. Most RAG demos gloss over the vector database, yet it's the single component that decides whether your answer is grounded or a total hallucination. Let's lock it in. The vector database stores the embeddings of all your documents. When a query comes in, its embedding is compared against those stored vectors, using cosine similarity, to find the chunks that are semantically closest. Without that rapid similarity search, the retriever couldn't deliver the right context in time. Before your AI can retrieve information, your documents must be prepared correctly. Start by splitting documents into meaningful chunks, usually a few hundred tokens with a small amount of overlap. So important context isn't lost at chunk boundaries. Each chunk is then converted into an embedding using the embedding model you've selected. Those embeddings are stored inside a vector database where they can be searched efficiently. Chunk size, overlap, document quality, and embedding model all influence retrieval accuracy. There isn't a single perfect configuration, so testing different settings against real user questions is an essential part of building a high-quality RAG system. Here's a practical roadmap for building your first RAG application. First, gather the documents you want your AI to understand, such as policies, runbooks, manuals, or knowledge base articles. Next, split those documents into meaningful chunks that preserve context. Then generate embeddings using an embedding model that provides the right balance of quality, latency, and cost for your application. Store those embeddings in a vector database so they can be searched efficiently. Connect the retriever to your language model using a framework such as LangChain or Llama Index, and build a prompt template that instructs the model to answer only from the retrieved context. Finally, test with real user questions, evaluate the results, and continue refining your chunking strategy, retrieval settings, and prompts. Building an effective RAG system is an iterative engineering process, not a one-time configuration. Imagine a systems administrator trying to remember the exact procedure for resetting a VPN certificate. Searching the company wiki returns dozens of documents containing similar keywords, forcing them to manually open page after page, looking for the right instructions. Now imagine asking the same question through a RAG-powered assistant. Instead of returning a list of documents, the assistant retrieves the most relevant procedure from the knowledge base, summarizes the required steps, and provides links to the original documentation for verification. The result is faster problem resolution, fewer interruptions, and much less time wasted searching for information. Now imagine applying that same idea to an IT help desk. A Level 1 support technician receives a ticket describing an unfamiliar VPN error. Instead of manually searching dozens of knowledge articles, The technician enters the issue into a RAG-powered assistant. Within seconds, the system retrieves similar historical incidents, the most relevant troubleshooting guide, and the documented resolution steps. Many organizations have reported improvements in ticket routing, knowledge reuse, and support efficiency by combining AI with well-maintained documentation. The language model isn't replacing your documentation. It makes your documentation dramatically easier to use. Building a production RAG system involves several layers that work together. Frameworks such as LangChain and Llama Index help orchestrate document loading, retrieval, and prompt construction. Vector databases like Chroma, pgvector, Weaviate, Pinecone, and Milvus provide fast semantic search over millions of embeddings. Managed AI platforms including Azure AI Foundry, Azure AI Search, Amazon Bedrock Knowledge Bases, and Google Vertex AI Agent Builder bundle many of these capabilities into integrated services. Understanding the role of each layer helps you design architectures that match your organization's requirements, regardless of which products you ultimately choose. Checkpoint: RAG tools. At this point, you've seen the major building blocks of a RAG system. The next question isn't how it works, it's how you want to deploy it. Some organizations prefer to assemble every component themselves for maximum flexibility and control. Others choose managed platforms that reduce operational overhead and accelerate development. Neither approach is inherently better. The right decision depends on factors like your team's experience, security requirements, compliance obligations, operational resources, and how quickly you need to deliver value. As you evaluate RAG platforms, think beyond features. Consider the long-term cost of operating the solution. Here's the trap many beginners fall into. They assume RAG is magic, and that simply plugging in any documents will fix everything. It won't. If your knowledge base is a mess of outdated PDFs, duplicate pages, and poorly scanned images, the retriever will bring back garbage. If your chunks are too large, critical details get diluted. And if you use a weak embedding model, the vector search won't capture true semantic meaning. It'll just match keywords. RAG amplifies the quality of your input data. It doesn't fix it. So before you build the pipeline, invest time in curating clean, well-structured, and accurate documents. Checkpoint: RAG quality factors. Retrieval quality depends on much more than simply storing documents in a vector database. One of the biggest factors is chunk size. If chunks are too small, important context gets split apart and the retriever may miss the information needed to answer the question. If chunks are too large, the most relevant details become buried inside unnecessary text. Most successful RAG systems find a balance by creating chunks that preserve complete ideas while remaining focused enough for accurate retrieval. The optimal chunk size depends on your documents, so it's something you should measure rather than guess. Improving retrieval doesn't stop there. Even after the retriever finds relevant documents, production RAG systems often perform one more optimization before sending context to the language model. This step is called re-ranking. A re-ranker examines the retrieved candidates using a more sophisticated model and reorders them by relevance, ensuring that only the strongest supporting evidence is passed to the LLM. Retrieval finds good candidates. Re-ranking helps identify the best ones. Together, chunking and re-ranking are two of the most effective ways to improve answer quality without changing the language model itself. So when should you actually use RAG? Walk through this decision tree. If the answers have to be grounded in specific documents that change over time, like policies, runbooks, or product specs, RAG gives you live retrieval with zero retraining. If the answer's no, check whether your data is static and you already have high-quality labeled examples. That's fine-tuning territory. And if all you really need is to steer the model's tone or format, prompt engineering alone can handle it. The point isn't to pick the fanciest tool, it's to pick the right one for the job. Once you understand the RAG ecosystem, the next architectural decision is whether to manage the platform yourself or use a managed service. Managed platforms reduce operational overhead by handling indexing, scaling, embedding generation, infrastructure, and many operational tasks for you. They're often the fastest path to production and are a great fit for many organizations. A self-managed architecture gives you full control over every layer of the pipeline, from document ingestion to vector storage and retrieval, but it also means your team is responsible for deployment, monitoring, scaling, security, and ongoing maintenance. Neither approach is universally better. The right choice depends on your security requirements, operational expertise, budget, compliance obligations, and how much flexibility your organization needs. Now it's your turn. Pick a small collection of documents you already use every day, an IT runbook, internal procedures, or technical documentation. Build a simple RAG application that chunks the documents, generates embeddings, stores them in a vector database, and answers questions using retrieval. Then test it with real-world questions. Which answers were accurate? Which ones failed? Experiment with different chunk sizes, embedding models, and retrieval settings to improve the results. This isn't just another coding exercise. It's the beginning of a portfolio project that demonstrates practical AI engineering skills employers are actively looking for. Let's lock it in. Pause and answer this. In one sentence, how does RAG improve large language model outputs? Ready? The key: RAG injects relevant, up-to-date documents right into the prompt, so the model is forced to base its answer on facts from your data, not just its frozen training memory. Today, you've learned how Retrieval Augmented Generation transforms a language model into a system that can answer questions using your own knowledge instead of relying solely on its training data. You now understand the 5-step RAG pipeline, how embeddings, vector databases, retrievers, and language models work together, and how to begin building your own solution. Your next step is simple. Build a small RAG application using documentation you already have. Then measure how changes in chunking, retrieval, and prompt design affect answer quality. Once you're comfortable with the basics, explore more advanced techniques like semantic chunking, re-ranking, and hybrid search to make your system even more accurate and reliable. That's exactly where we'll go next as we continue building production-ready AI systems. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.